Hi class, we're going to talk about our final topic in this section, curvature. So if you look at this figure here, from figure 4 below, you can see that the unit tangent vector t, changes direction very slowly when t is fairly straight, like here. It's the unit tangent vector is in purple here, is changing very slowly, but it changes more quickly as c bends or twists more sharply. Like you see here, it goes whoosh, whoosh, turning real quickly. The curvature of C at any given point is the measure of how quickly the curve changes direction at that point. So like right here, the curvature would be lower. Here, its curvature would be higher. Specifically, we define it to be the magnitude of the rate of change of the unit tangent vector with respect to arc length, So because the unit tangent vector has a constant length, only changes in direction contribute to the rate of change of this unit vector t. So then that means the curvature of a curve is given by the following. So we define curvature as the letter k is equal to the magnitude of dt with respect to s, dt over ds. This is where t is the unit tangent vector. So the curvature is easy to compute if expressed in terms of the parameter t instead of f's, obviously. So we can use the chain rule to write the following, dt is equal to dt over ds, ds dt, and then you can then see that the curvature is equal to dt over ds, which is dt over dt, ds dt. Now we can figure these out because we can take the derivative of the unit tangent vector with respect to t, and remember s is just the unit, the arc length function, so we're going to take that with respect to t. So then we can see that ds dt is just equal to the magnitude of the derivative of the function with respect to t. So this is the final equation you get. Curvature is a function of t, which is equal to the unit tangent vector's derivative, the magnitude of that, divided by the magnitude of the derivative of our vector valued function. So let's just do one example real quick. Let's show that the curvature of a circle of radius a is just equal to 1 over a. So we can take the circle we have centered at the origin, and then parameterization is the following. R of t is equal to a times cosine of ti plus a times sine t of j. That's just in 2 dimensions because we're only talking about a circle, not a sphere. So therefore, we obviously see that r prime of t is equal to minus a sine of ti plus a cosine of tj. And then if you were to just take the magnitude of this, you'd get the square root of this squared plus the square root of plus this squared. So you get sine squared of t, cosine squared of t, that's equal to 1. And then these a's would end up just, when you take the square root, just get you, because you'd have a squared, when you factored them out, would just be a. So therefore, the unit tangent vector t is just given by this simple formula here. We know it's r prime of t divided by the magnitude of r prime of t. Well, the magnitude of r prime of t there is just 1. So this is obviously then what the derivative of the unit tangent vector is. It's just the following here. So then thus by this equation, you can see that the magnitude of the unit tangent vector is just equal to 1. So the curvature of this circle, just by plugging it straight back into the formula, is just equal to 1 over a. All right, class, that was just a quick video, and when you get to curvature problems, just remember this formula right here, and they should be pretty straightforward to solve.